Okay.
Our next speaker is Sergio Bacallado. He used to be at Stanford and worked with Percy Diaconis, and now he's sitting just across the lawn.
Thank you, Peter, and thank you to all the organizers for inviting me to speak. Can everyone hear me? Is it okay? So my talk, the reason I started working on this problem was because I was considering the question that Peter Hoff asked in his talk. You know, why is it important to do things in a Bayesian way when we're analyzing networks? Okay, so typically the obvious answer is if we care about inference of any problem, then having a notion of uncertainty is important, and hopefully the posterior is a good measure of that uncertainty. Okay, but if you think of the value of the posterior when making decisions, and in particular when making sequential decisions, then I think a Bayesian method really is really worth it. Okay, because it can really improve the efficiency of various sequential procedures. And so I'm going to tell you about sequential matrix completion. This is joint work with a master's student here, Annie Marston. And so I'll tell you a little bit about bandit problems, okay, which is the framework in which I'm analyzing sequential matrix completion. And then I'll mention a couple of algorithms that are common for bandit problems, the upper confidence bound algorithm and Thompson sampling, which is a Bayesian idea. And this is really the main result I'm going to show, which is an experimental evaluation of Thompson sampling for sequential matrix completion. And then finally, I'll conclude with some considerations on how to do regret analysis for matrix completion. Okay, so let me start by telling you what a bandit problem is. So the multi-armed bandit is a classical problem in statistics and operations research. And the idea is that we have n actions that we can take. So these are like arms in a slots machine in a casino. And at each step t, we have to pick an arm, which we're going to call A of t. And we obtain a reward, RT, which has expectation f of AT. So the expectation, each arm has some mean reward, which we call f of A. And our goal is to find a policy, so a sequence of arms that we're going to pull, using information about the previous rewards that we've seen, such in order to maximize the total reward that we obtain after a finite number of steps. Okay? So this finite number of steps is what we call the horizon. And a straightforward generalization of this problem is what is known as the linear bandit. And the idea here is that the expected reward for an arm is a linear function. Okay, so you have some vector of features for every arm, which is called phi of A. And then you have a vector of parameters theta, and the expected reward is this inner product between those vectors. Okay, so here we have some correlation between the arms. So when you pull one arm, that gives you information potentially about the reward for different arms. And that might change your strategy. And you can generalize this to obtain what is known as a generalized linear bandit. And the idea here is that you pass this linear form through some inverse link function, and that gives you the expectation of a reward that is usually in some exponential family. Okay, so abstractly, how can we understand these bandits? So we have some action set A, which is not necessarily finite. So you could have infinitely many arms. You have some parameter in d dimensions, and some reward function, which for each value of the parameter theta, which maps from the set of arms or actions onto the real numbers. Okay. We're going to define the optimal policy, okay, which is the policy that gives you the optimal reward, okay, if you know the true parameter theta. And then we're going to consider how a sequential policy behaves. So now if you choose a sequence of actions through some rule which takes into account the history of rewards that you've seen up to time t, that's what we're going to call A of t, this sequential policy. And the quantity that we're typically, that we want to minimize is what is known as the regret, okay? And the regret is simply the expected difference in the total reward of the optimal policy, so if you pick the optimal arm each time, versus the expected reward of our sequential policy, A of t. Okay, this is the regret of this policy for a specific value of the parameter theta. Yes?
To be clear, so the reward distribution is not changing over time, or at least its expectation is not changing?
The expectation of the reward distribution is not changing over time. Yes. I'll make a slight modification in the next slide. But yeah, in a classical bandit problem, the average reward for each arm is the same at each step. Okay, so we might care about the worst case regret, which is like a minimax idea, where if we maximize this quantity over all possible values of a parameter, that gives you the worst case regret.
So why is A star t a function? Why does it depend on t? Is it the best policy the same at every time?
Yes. So if at each step you're allowed to choose any arm, then that's true. There's one optimal arm, and this wouldn't depend on t. But here I'm allowing for the possibility of restricting the set of arms that you can choose from at each step. Okay, so that's why I let A star depend on t. Okay, and so we can maximize the regret, but we can also take the average of the regret over some prior distribution of the parameter, and that's what we're going to call base regret. Okay, this gives you a notion of average case loss. Okay. Okay, so this is what a bandit problem abstractly, and how can we fit sequential matrix completion into this framework? So I'm sure we've all heard of a recommender system. So this is an idea that's been heavily studied in the last few years. We have a group of N1 users and N2 products. Each user gives a rating to every product, and we're going to call xij, so that the ijth entry in the matrix X is the rating that user I gives to product J. Okay, and there's a variety of models that allow us to predict missing entries in this matrix based on the assumption that the matrix has low rank. Okay, so the problem that we're going to consider is what is the best sequence of entries that we need to choose if our goal is to find the largest entries in the matrix as early as possible. Okay, so here the action set, or the set of arms, is a set of indices for entries in this matrix. The parameter is the matrix itself, which we're going to assume is of low rank. We're going to, so the expected reward function, the reward for taking the action ij is just the ijth entry in the matrix. Okay, and you can write this in this way. If this is a rank R matrix, and this is the inner product of two vectors of length R, right? So this shows you the connection with a linear bandit. Okay, so in a linear bandit, you would assume that you have some features for J, say, but here you would have the parameter theta, which is fixed. It does not depend on the row of the matrix, okay? And we're not assuming that we know what this feature mapping phi is. Okay, so this is a non-trivial generalization of the linear bandit. And then we're going to also introduce this idea of discounting, okay? So if you think of a recommendation system where you're recommending products to users, perhaps when you recommend the same product to the same user twice in a row, the second time you expect to have a lower reward. So that comes to the problem you brought. So what if the expected reward for a specific action is decreasing every time we choose that arm? Okay, so we're considering this form of geometric discounting. So we're multiplying the expected the reward for the first time you see an action times some parameter gamma between 0 and 1 to the power of the number of times you've seen that action, you've chosen that action before in your policy. Okay, so this is a slight generalization or slight deviation from the classical framework. Okay, so what kind of applications does this have? So recommender systems have many applications, especially in targeted advertising online, recommending content in different content platforms. So, of course, the Netflix problem is the example that everyone likes to talk about with matrix completion. And also in network models, Peter discussed matrix factor models or latent factor models for networks, which have this low rank structure. And if we think about suggesting connections in this network in a sequential manner so that we see the biggest entries first, then this falls into our framework. Okay, so for example, suggesting missing links in a social network could be an application of this. Okay, but this is really quite a general framework. So anytime you have a sequential decision process where your decisions are indexed by the Cartesian product of two sets, which are not ordered, things fall into this framework. Okay, and it's easy to generalize it in different directions. So you could incorporate known features for the rows or the columns of the matrix. So you could have these random effects that we had previously, but also add some effects that are specific to the column and the row. You can also define generalized rewards with an exponential family distribution, as in a generalized linear banded. And if you have, if your decisions are indexed by more than more than two indices, say you have 3 indices, maybe you can use a low-rank tensor factorization as opposed to a low-rank matrix factorization. So I think this is a simple problem to study, which has many different generalizations. Okay, so how can we choose these actions now? Okay, we have to find a policy to choose a sequence of entries in the matrix. And what are some usual choices for this? So the first choice that I'm going to talk about is the upper confidence bound algorithm introduced by Lai and Robbins. And the idea is very simple. After taking t actions or t minus 1 actions, we build a confidence interval for the reward, the average reward at each arm. Okay? And then the action that we take at step t is the one that has the largest upper confidence bound. Okay, and here we take into account the discounting that I mentioned earlier. Okay, so we're going to take the action that has, if you think of the upper confidence bound as the best possible reward that you could see from that arm, we're going to maximize over that best possible reward. Okay, and you'll notice that an action is likely to be chosen if the estimated reward is very large. Okay, so if you've seen that action many times and your expected reward is large, then you're likely to choose that action, and that encourages exploitation of arms that we know are good. But if there's a lot of uncertainty in the reward for this action, then the confidence interval will be broad and the upper confidence bound will be high, and so you can also, that also increases your chances of picking an arm, and that encourages exploration. So this is how this algorithm balances the exploration-exploitation trade-off. Okay, but a problem is that it is often difficult to find a confidence set for the function which has good coverage when there's complex dependency between the arms. And even when you can define a confidence set, it can be hard to compute the upper confidence limit for a specific action. Okay, so often UCB algorithms can be useful in theory, but not so good in practice. Okay, and even when you can find a confidence set which has good coverage, maybe it's much wider than what you really need, and so it's inefficient to use it in a banded design.
Can you do it with Bootstrap or something without being very clever?
Yes, so you can use bootstrap sample splitting methods to do a UCB, but that's often not better than using posterior credible intervals, for example.
What confidence level do you use Like 95% or 90% or?
So that's a parameter in the, you can optimize over that. Yeah. Okay, so the second method I wanted to talk about is Thompson sampling. Again, this is a Bayesian idea. It is not a Bayes optimal method. So what we call a Bayes optimal method is one that has the smallest Bayes regret. And that is typically an intractable dynamic programming problem, and that can't be solved. But Thompson sampling is a Bayesian heuristic idea in the sense that it's using the posterior distribution. So let me describe what it does. We're going to put a prior pi on the parameter space, in this case our low rank matrix. And at each step, we choose an action with the probability that it gives you the largest reward on average. Okay, so the probability that the action chosen at time t is A is the probability that A maximizes our expected regret. Okay? And so like the UCB algorithm, this encourages exploration in arms where there's more uncertainty, but also exploitation when you can be quite sure that an arm is the optimal one over your set of possibilities. Okay, and this has the advantage that when there are complex dependencies between arms, this is a lot easier to implement than the UCB. And it can be more efficient when the credible intervals are a good representation of your uncertainty. Okay, so let me describe one option, okay, one model that we can use as a prior for our low rank matrix, and this is a gamma process factor model. So I think that it's easier to understand the model if you formulate it in this way. X will be a low rank matrix plus some IID noise on the entries. And these factor matrices W and V have the following prior. V is a Gaussian matrix with IID entries, and W, this factor matrix W has the property that only a few of the columns will tend to be big. Okay, and you'll notice that the rank of this this matrix W V transpose is capital K. That's the maximum possible rank, but the effective rank of the matrix can be smaller, and that is tuned by these parameters Rk, theta naught, and C naught. Okay, so this is a sort of non-parametric model in the sense that it adapts to the true rank of the matrix. Okay, so our goal will be to evaluate how well Thompson sampling works when you're using this model for the low rank rewards.
Maybe you just said this and I missed it, but so this is going to be, you're doing a gamma prior on the W's, and which has a certain sort of tail behavior or concentration near zero, whereas you don't have that for V. You have this asymmetry and sort of that potential for adaptation depending on the rows or columns.
Yeah, the idea is that so if you think of the singular value decomposition of this, the singular values are shrunk by the fact that the columns of X, only a few of them will be large. And so
If you made the V's gamma, would that?
yeah, that would also, I mean, you could do the same thing for V, but it's not really necessary because you're already doing this sort of regularization through the W. Yeah.
Question here too. So this is for a different problem than your recommended system problem, though. Your X is the matrix of counts.
So we're assuming that X, in this case, is a real number. Yeah, it's a real value matrix. But I think you could link that expected reward. If your observations were ordinal, for example, you could use a sort of generalized linear model type idea. Okay, so we're going to apply two inference methods to be able to sample the posterior distribution. The first one is a stochastic variational inference algorithm, and I'll just go through this very quickly. The idea is we're trying to find some simplified distribution that approximates the posterior by minimizing the KL divergence between the posterior P and our candidate Q. We apply mean field type of approximation, which allows for correlations between the factors for each row of the matrix W. And the way we solve this optimization is through a stochastic optimization method that's been developed over the last few years by a number of authors, and these are probably the two most relevant references for what we're doing. And then the second inference method that we're going to use is one that is asymptotically unbiased. So variational inference in the limit, if it converges, it'll give you something that may not look a lot like your posterior. This algorithm is more like a standard MCMC. So this is developed by Welling and Te. What we're doing is a discrete approximation of the Langevin equation, the stochastic differential equation, which has the posterior P as a stationary distribution. And we make two approximations. So the first is we use stochastic approximations of the gradient. And we don't metropolize, as in the Langevin algorithm. So when you solve this equation numerically, you introduce errors, and typically you have to use Metropolis-Hastings corrections. But we avoid that by using a schedule of step sizes, which is decreasing. So this prevents asymptotic bias. There's recent work that suggests that it may be better to use the discretization of this equation with a fixed step size. Okay, but we're using a decreasing step size. Okay, so let's see how well Thompson sampling works if we use this prior and these inference methods. So we're going to simulate a random reward matrix, just taking the outer product of Gaussian matrices. And in each case, we're going to apply the following three algorithms: Thompson sampling using the variational inference approach, Thompson sampling with the stochastic gradient Langevin dynamics method, and also a heuristic strategy in which every certain number of steps we obtain an estimate of the low rank matrix using a singular value thresholding algorithm, and then we greedily sample the largest entries in that matrix. Okay, and so let me show you these simulations. And so here, what you're seeing is the cumulative regret as a function of the number of entries that you observe. You'll notice that, so in red you have the heuristic method, the blue is the stochastic variational inference method, and in green you have the Thompson sampling method. And this is where the true rank of the matrix is 5. And we also repeated the simulations for increasing values of the rank of the matrix up to rank 20. Okay. And what you see is that the Thompson sampling with the Langevin dynamics method really works a lot better than the other two methods for every rank. But the interesting part of these plots is really before this stage. You'll notice that at this stage, the heuristic method starts to work about as well as the other two. And that's because that's the matrix completion threshold. So if you look at the errors that are made by these three methods as a function of the number of iterations, you'll see that there's a threshold where we've seen enough of the matrix that we can fill it up completely. And the error of the three methods goes down to 0. For the Bayesian methods, you have to observe a few more entries. That's probably the price you have to pay for not sampling entries uniformly. Okay, but really we're interested in the regret of these methods before we hit this detection threshold, because after this threshold, presumably we know the matrix with enough confidence that we know what the optimal sequence of actions is. And so if you look at the curves for rank 20, the detection threshold falls around here, and you see that before this threshold, the Bayesian methods do better than the heuristic method, because you're using a notion of uncertainty in the entries of the matrix that is specific to the entry in the matrix. Okay, the uncertainty in the entries, in the missing entries of the matrix will not be the same for different entries, and that's what the Bayesian method is capturing. And you can see that if you look at the sampling masks at different time points for Thompson sampling, you see that there are rows and columns that are heavily oversampled initially. So it's like you're filling up quadrants of the matrix and exploiting in those submatrices before you start sampling other entries. Whereas the singular value thresholding method just samples uniformly initially until it hits the detection threshold, and then it can sample the optimal sequence. Okay, so main observations, we're interested in finite horizons before the matrix completion threshold. You can think of this as the case where we have infinitely many products and customers, right? So in a lot of applications, like online advertising, you have so many nodes, you have so many products and so many customers compared to the rank of the matrix that really it would be quite hard to even hit the detection threshold, to hit the threshold where you can complete the full matrix. Okay? And if you're in this regime, you're balancing exploration and exploitation within the rows and columns that you've sampled with this necessity of adding new products or adding new customers. And this is related to the infinitely many armed bandit idea. And Thompson sampling seems to effectively balance these requirements between exploration, exploitation, and discovery. And we find that the stochastic Langevin method outperforms the variational inference method, and it's actually less costly computationally, because at each step of the bandit, we only need one sample from the posterior in order to do Thompson sampling. Okay, so I only have 2 more minutes, so I'll explain the idea of this method where, let me just jump here. So we're using an idea from a paper by Russo and Van Roy where they show a general approach to bounding the base regret of a Thompson sampling algorithm. And the idea is you decompose the regret in this way. And you have one term that is smaller than 0 with high probability and one term that is smaller than the width of a confidence interval with high probability. Okay, so if you have, as long as you're able to define a confidence set which has good coverage guarantees and which contracts quickly on the actions that you choose, then you can show that the base regret, no matter what the prior is small. Okay? This is the base regret where you're looking at a Thompson sampling policy with respect to some prior, and then you're averaging the regret with respect to the same prior. So this is a type of self-consistency property. So we've explored how to bound this regret, and we obtain a bound of this form, which is based on a theorem by Russo and Van Roy. And at this point, we don't have a very strong estimate of these constants, and I won't have time to go into much detail here, but I'll just mention what the main problem is. These constants have to do with the width of confidence sets and the correlation between the rewards for different arms in our model. And the difficulty in bounding these in the matrix completion setting is that a lot of theory in matrix completion assumes 2 things. You assume that you have some sort of uniform sampling of entries, which is clearly broken down if you're doing a sequential design. And then you characterize the error in terms of average notions of error. Okay, so you have average notions of error, and here we really need entry-wise notions of error. And so we've made some progress in bounding these constants, but there's still a lot of work to do. So let me just conclude. There's low-rank matrices are a simple framework to study complex dependencies between arms in bandit models. I think this is quite general, for the same reason that factor models are general in the sense that Peter described. Bayesian algorithms perform quite well in practice before you hit the threshold for completing the matrix, which is interesting. And the analysis of regret is complicated by the fact that a lot of matrix completion theory assumes a random design and average notions of error. There's some potentially useful work by Kirali, Turan, and Tomioka, where they apply algebraic techniques to understand which entries in the matrix can be completed from a partial set of observations. But there's much room for theoretical work. It seems quite difficult, but it would be very interesting to obtain bounds for horizons below the completion threshold, or to develop heuristic methods based on the observations from Thompson sampling that scale to massive data sets. And also the problem of understanding the rank adaptation behavior of Thompson sampling, which we observed experimentally, seems very interesting. And finally, obtaining regret bounds with action-specific discounting, like in the way that I framed it, seems pretty challenging and non-standard, but I think it would be important in applications.
Can you say a little bit more about what is a Luder dimension? Is there any intuition, like is it like VC dimension or some other dimension?
It's actually not like VC dimension, so I have a definition here in English. So it's the length of the longest sequence of actions, so the longest sequence of entries that you can choose in a matrix, such that no entry in the sequence is predictable given the previous entries in the sequence. Okay? And by predictable, I mean predictable to some degree of accuracy, which is this epsilon.
Can the actions be chosen very poorly?
Yeah, so you're supposed to choose it adversarially, right? So it's the longest sequence that you can choose, such that no sequence is predictable from the previous ones, right?
Like in a low-rank matrix, if you chose the actions strategically, is there some way you could get a covering so that you could cover all, you could determine all low-rank matrices? Or are the results like, or if you choose them all just to be on the same row, that might be adversarially?
Yeah, so I can tell you sort of how we proved this bound. So this is combining a result from extremal graph theory with some perturbation bounds and matrices. And so the idea is, there's this theorem, the Kováry-Turan theorem tells you that if you have a bipartite graph, which is what our matrix of, or what our mask is, if you have a bipartite graph with enough edges, then you need to have a biclick hidden somewhere, right? And so if you have a biclick of length r plus 1, then the last entry that you observe in that submatrix is predictable from the previous ones, and you can bound exactly the error in that last entry. Okay, so that's one approach, but of course you don't need to have a complete r by r plus 1 times r plus 1 submatrix. You can find better designs, but it seems like quite a difficult problem.
Maybe one more quick question.
There's quite a lot of recent work on optimization for Gaussian processes using expected improvement. I mean, you've got something which is like expected improvement or expected optimal regret. I wondered if you're aware of that area and whether these methods would be at all relevant to it.
Yes, I mean, perhaps you're referring to the area of Gaussian bandits.
Well, no, this is just finding optimum. You have a Gaussian process.
Yes. So if your reward function is a sample of a Gaussian process,
yes.
Then that is an interesting point of view.
And so you naturally get correlations, obviously, because you're working on a correlated Gaussian process, could be relevant.
Yes, I think there may be connections between Gaussian processes and this. Gaussian bandits and this. Yeah. So if you think of the kernel of the Gaussian processes, telling you about the correlation of two entries in the matrix, you could pose the problem in that way.
All right. Thank you very much. So we have a 1-hour lunch.